Okay, so let's talk about fluid replacement. Fluid replacement is exactly what it sounds like. It's fluid that we give to replace something that is lost in the body. We give it through IV. It goes straight into the patient's circulatory system because it's going right into the vein, right? And so depending on what we give, it can replace only fluids, or it can replace some electrolytes, or it can cause some shifting between compartments. And we'll talk about how that happens in just a minute. The takeaway from this slide is really just that there are two different types of fluid replacement. We have crystalloid fluid replacements, and we have colloid. Really the difference here is that crystalloids contain smaller particles like electrolytes, while the colloids have much larger particles, larger proteins. The most popular one is albumin that we give. And so let's just look at this colloid first for a second, really quickly. So let's imagine that we're giving albumin. So we've put into the patient's vein a bunch of fluid with some, let me just see what I can do here, with some albumin in it. So we've got lots of albumin inside of this. Might have a little bit of albumin out here. We might even maybe have some in a cell, but unlikely. It's very large. But anyway, doesn't really matter. The point is that what happens when we give this albumin? Well, it changes the oncotic gradient between what's in the intravascular space and what's in the rest of the extravascular space. And so what happens is we've got some oncotic pressure that we've created, and now that fluid is going to be pulled towards that albumin. You have to remember that it's not only about the amount of particles that are in a fluid, it's also about the size. The fluid is very attracted to the larger the particle, the more attracted the fluid is. So albumin plays a huge role in controlling fluid shifting between compartments. And so it can be a very important fluid replacement to give. Sometimes we do give albumin simply to replace albumin loss for certain reasons. We'll talk about in other units. The body can lose the albumin or can lose its ability to create albumin, and so we may just have to replace the albumin. So that may not necessarily change a gradient, but it will rebalance that gradient. Okay, so other than that, I wouldn't worry too much about the colloids, because most of what we're talking about are these crystalloids, and we've actually already talked about them when we were talking about isotonic, hypotonic, and hypertonic formulations. That's what we were talking about. These have electrolytes or smaller particles in them. Everything else that's kind of under this heading is going to be discussed in the next slide. So I'm just going to skip through. You don't have to worry about that, because really the takeaway from here is the difference between a crystalloid and a colloid. And remember that crystalloids are the ones that we're usually giving, that we've been talking about, that are isotonic, hypotonic, and hypertonic. How do I get to the next slide? Oh, we're still recording, are we? Haha. There we go. Okay, so this slide is just showing you those types of crystalloid that we talked about earlier, crystalloid solutions. So we have the three different kinds. We have the isotonic, hypotonic, and hypertonic. Let's talk about isotonic first. Isotonic means that the ratio of particle to fluid inside of that kind of bag of fluid that we're giving is the same as what should be the ratio inside of the body. And so when we give an isotonic solution, it really doesn't change the movement between, it doesn't change the gradient between these spaces, and therefore it shouldn't change the movement of fluid between the spaces. What it should do is simply fill up or give more fluid to what's in this specific space, which is the intravascular space. And that's why we give this often for hypovolemia, because really what we want to do is just replace the fluid that's been lost in the veins. We need the heart to keep pumping. We need everything to keep moving, and so we will increase that. We will increase that fluid. There are three kind of main types of normal or isotonic solutions. The main one is your 0.9% sodium chloride. This is your normal saline. This 0.9% of sodium chloride gives you the same kind of ratio of particle to fluid that is in the body. And so it doesn't change, again, it doesn't change this gradient. It just goes in and fills this space because it's giving you a solution that has the same osmolality as what's already in here and what's here. And so it's not going to move. The fluid's not going to shift. So normal saline at 0.9% in that bag is what gives us that ratio. Another one that is isotonic that's often given is lactated ringers, or Ringer's lactate, or Ringers, it doesn't really matter. Again, it's got the same percentage of particle to fluid, only Ringer's lactate has not just normal saline, it has a bunch of other electrolytes as well. It has potassium, has a few others. It still has that same gradient of particle or a ratio of particle to fluid. So when we give it, it's not going to shift fluids. It's just that instead of those particles being made of only sodium, they're also made of potassium and phosphate and a couple other things that we need. Think phosphate. Doesn't really matter. It's a bunch of other electrolytes. And then we have your weird, troublesome friend D5W. So D and the 5 stands for 5% W. So it's 5% dextrose in water. And again, this D5W, it doesn't, the dextrose in there creates an osmolality that is very, very similar to what's already in the body. So once we give it, and we've got, it's full of kind of little, dextrose. At this point, it still has the same osmolality, so there's no shifting happening between the compartments. However, these dextrose particles or what have you are metabolized very, very quickly by the body. So the body uses them up, right? It turns to glucose, so glucose used for energy. And so they very, very quickly disappear out of this fluid. And that's why sometimes D5W is called an hypotonic solution, because once these particles are metabolized and gone, we now have a whole lot less particle in here than we did. And so now what we've given after that dextrose has been metabolized is actually there are less particles in here now than there are out here. And so it will actually cause a shift in the gradient. We'll talk about hypotonic in a second. But that's why you'll see D5W on lists for hypotonic and lists for isotonic. Most of the time, however, you're going to see it listed as isotonic. And so your three kind of main isotonic solutions are going to be your 0.9% sodium chloride, right? Sorry, Cl. Your ringers lactate or lactated ringers, and your 5% dextrose in water. These are your isotonic solutions. So let's talk about hypotonic solutions. We already know, we've talked about what happens when we give a hypotonic solution into the vein. Well, we've got a gradient inside that is less than or lower than what is outside. And remember that we're not just talking about that, we're talking about the difference between all three of these spaces. So here we've got the intravascular, here we've got the interstitial, but don't forget we also have cells, and we have cells that are inside the blood as well. We still have, this is still intracellular. Even though it's in the vein, it's still a cell inside of that intravascular space. So the fluid still has to move through this membrane to get in and out of that cell. It's still moving compartments, right? From the intracellular space, even if that cell is a red blood cell, into the intravascular space. And that's why the picture here is showing, these pictures are showing red blood cells. It's showing you just a shift from one compartment to another. So let's imagine that. I'm going to draw another kind of bigger red blood cell here. We've given a hypotonic solution, meaning there is the solution that we've given in the vein has a lower tonicity. It has less particles in it than what is inside the cell or inside the interstitium, one or the other or both. What's going to happen? Well, we know the fluid is going to move towards the place where there are more particles. It's going to move from the area of low to high concentration. Because of that oncotic pressure, the fluid is going to then be pulled towards the places where we have more particles. So it's either going to be pulled into the interstitium and or into the cell. These solutions are really, really important when we have cellular dehydration, when the actual cells have been dehydrated, because we need to pull fluid into that space to keep those cells from drying up. Of course, we have to be very, very careful. We're not moving too much so that it completely explodes like this lovely picture here, which is one of the reasons we're going to be very, very careful when we're giving hypotonic and as well hypertonic solutions. Anytime we're making the fluid shift like that, we have to be very, very careful. So we know that hypotonic solution is going to move the fluid from an area of low concentration, high concentration. So it's going to move into the cells or into the interstitium. What kind of fluids are hypotonic? This is really, really easy. So we said 0.9% inside of that bag that we're giving. If 0.9% of that is, 0.9% of that is sodium chloride, is the isotonic, is the normal ratio, then it's really, really easy because a hypotonic is actually 0.45% sodium chloride. This is a hypotonic solution. It has less sodium chloride than is normal, right? So it's easy to identify. The same with D5W. D5W comes in D.225, I think, or 0.25 in water. So you can see that this amount of dextrose is a heck of a lot less than this amount of dextrose. We know this is normal, so this has to be hypotonic. There's less in there. So any number that you see that is less than 0.9 normal saline or less than 0 or 5% dextrose in water is going to be a hypotonic solution. And likewise, you have solutions that are 10% dextrose in water. You have hypertonic, actually comes in 20%, in 50% dextrose and water. You can have a 3%, so 3% sodium chloride. 3% is much, much higher than 0.9%. So right away and 10% is much higher than 5%. So you can right away see that these are higher than your isotonic solution, and you'll identify them as hypertonic. So all you have to do is know these three, just know the isotonic solutions. And then depending on whether it's less or more, you'll know if the solution we're talking about is hypotonic or hypertonic. And we talked about what's going to happen if we give a hypotonic solution. Let's talk about what happens if we give a hypertonic solution. Again, we're putting into the vein, we still have cells in here, we have cells out here. We're putting into the vein something that has a lot of tonicity. There's way more here than there is in here or out here. So what happens? The fluid is going to shift. The oncotic pressure, the oncotic gradient, osmotic gradient changes. The oncotic pressure pulls the fluid towards the area with the most particles, because it's trying to water it down. It's trying to get this ratio in here to be the same as the ratio out here in order to maintain homeostasis. And so you have fluid shifting into the compartment with the higher tonicity. And in this case, it's going to be the intravascular space, because we've put a bunch of tonic or a hypertonic solution into those veins. So it's going to pull fluid. Not only is it going to pull fluid from the interstitium, it's going to pull it from the cells as well, right? And so your red blood cells here are going to have fluid moving out. That's why this picture shows it like this. And they're going to shrink and dry up. Now, if you start out with a red blood cell like this, then moving fluid out is great. It's just that we don't have a lot of control over how much fluid is moving out. And that's why we have to be very, very careful with a hypertonic solution as well. And again, especially with those dendritic neurons, right? If we pull fluid out of these neurons and we kill these neurons, those neurons aren't coming back to life, and we can cause severe mental disability or even coma and death.